So let's look at prime ideals. So an ideal P of R is prime if A times B in P must mean that you started with either A in P or B in P. So when you multiply two elements and land in your ideal, you must have started with one of those elements in the ideal. So let's do an example. PZ, here, P is going to be an actual prime number like 7. So all multiples of your prime number P is a prime ideal in this ring of integers. This is where the name prime came from. Why is this a prime ideal? Well, if you take two elements, integers, A, B, you multiply two integers, A and B, and you get like a multiple of a prime, the only way that can happen is if either A is divisible by P or B is divisible by P. So if you multiply two integers and end up with a multiple of a prime, then that means that either A is a multiple of the prime or B is. Let's do another example. So let this be the ideal of everything of the form x times P of x, where P of x is a polynomial with integer coefficients. So I'm going to look at every polynomial of this form. If you think about it for a second, this is the set of polynomials that look like an x to the n up to a1 x to the first plus no constant term. So I'm not going to write down a constant term. That's where the coefficients of your polynomial are integers. So this is an ideal. It's actually a prime ideal. In the ring of polynomials with integer coefficients. So it's not too hard to verify that if you multiply two polynomials together and get something with a zero coefficient of no x term, then one of the polynomials had to have had no constant term in the end. Okay, so here's the theorem. Here's the theorem concerning prime ideals. So let P be an ideal in a commutative ring R. So commutative ring R. Then P is prime if and only if the factor ring R mod P is an integral domain. This should remind you of our last video concerning maximal ideals. The theorem from our last video was M is a maximal ideal if and only if the factor ring is a field. So this is a related theorem. The proof of this theorem is easier than the one that we had in the last video. This one's just an unraveling of the definitions. So if you have a prime ideal, that's an equivalent condition to the definition. That means that whenever you multiply two elements and land in P, that must imply that either A was in P or B was in P. That's the definition. But you could rewrite this definition using terms from the factor ring. So that's true if and only if A plus P times B plus P is equal to 0 plus p, that implies that either a plus p is equal to 0 plus p, or b plus p equals 0 plus p. Why is this? Well, if you remember the definition of multiplication in the factor ring, this here is the same as ab plus p. So if you rewrite this condition using terms in the factor ring, that's saying that a times b is in p. So that would mean a times b plus p is p itself. So this underlined condition is the same as this underlined condition, just rewriting things in terms of cosets. A being in P is this condition, and B being in P is this condition. So I just rewrote everything in terms of the coset language. However, we're done. We're done. That's the definition of an integral domain. Remember what an integral domain means? When you multiply two terms together and get 0, that means one of the terms had to be 0. That's the definition of an integral domain. So that's true if and only if the factor ring R mod P is an integral domain. So that proof was much easier than the one for maximal ideals. Let's write down a corollary to finish this video. Corollary. Every maximal ideal in a commutative ring is prime. So here's the proof. Really, this is more of an observation, but the factor ring R mod M, if I have a maximal ideal, this is a field. So if I have a maximal ideal M, our last video proved that the factor ring is a field, and a field, that's an integral domain. So fields are subsets of integral domains. If the factor ring is an integral domain, then my ideal is prime. Okay, wonderful.